In this video, we shall try to learn two things. One is the need for carrying out some chemical reactions in solutions, and the other is the various concentration terms that are used to express the composition of a solution. Now, we all know that a chemical reaction is a reaction between the particles of the reactants. The particles could be atoms or molecules or ions. And obviously, a reaction between the particles of reactants can take place only when they come into contact with one another. And the particles of the reactants can come into contact with one another only when the reactants are thoroughly and uniformly mixed with one another. Then, depending upon the nature of the reactants, depending upon the conditions applied, a reaction between the reactants takes place at a particular speed. But if we don't mix the reactants uniformly, then certain parts of the reactants are separated or isolated from one another. Therefore, the possibility of a chemical reaction between those parts is eliminated or removed even if you apply the right conditions. Obviously, right? If the reactants are unable to come into contact with one another, then a reaction between them is not possible even if the conditions are right. So, if you don't want to waste any reactants, and if you want to carry out the reaction at a particular speed, you must mix the reactants uniformly with one another. Then you are providing an opportunity for the reactants to react with one another as much as possible. Similarly, in case of liquids also, we don't have to put much effort to mix them uniformly. Of course, there are some liquids that do not mix with one another, like oil and water, but liquids that mix with one another can be mixed uniformly with a little bit of stirring. This is our common experience. Then what about solids? We can stir a mixture of solids to mix them to some extent, but no amount of stirring is going to mix them uniformly. In that case, how do we carry out chemical reactions between solids? For example, between aluminum and iodine. And a reaction between them can take place only at their surfaces where they can come into contact with one another. And if one of the product formed is a solid, it might get deposited on these surfaces, and this covering or this deposit might prevent any further reaction between the reactants because it is coming in between the reactants. That means with time, the reaction slows down and eventually it stops. So it is difficult to mix solids uniformly with one another. Therefore, it is difficult to carry out sustained chemical reactions between solids at reasonable speeds. Then how do we overcome this difficulty? See, in some cases, we have no choice but to carry out the chemical reactions between the solids themselves. In those cases, we may use different techniques to overcome this difficulty to some extent. Sometimes we grind the reactants to a fine powder or finer crystals so that their surface area is increased. Thereby, more and more amounts of the reactants can come into contact with one another. In some cases, we constantly stir the reaction mixture. In some cases, we maintain a higher temperature. So, by using different techniques, we can overcome this difficulty to some extent and carry out certain chemical reactions between solids. But in many cases, we have a simpler solution. See, the reason why it is difficult to mix solids homogeneously is because in solids, the particles they are composed of are almost firmly held in their positions. They are not free to move from one point to another point in space. The attractive forces between these particles do not allow them to move away from one another. Whereas in case of gases and liquids, the particles they are composed of are free to move from one point to another point. That is why it is easy to mix gases and liquids that mix with one another rather easily. So if that is the case, we can use the same strategy to mix reactants that are solids as well. See, as we just discussed, it is not a good idea to mix these solids directly with one another to carry out a quick reaction between them. Then what can we do? Lead nitrate mixes with water. When you add lead nitrate to water and stir the mixture, somehow water breaks the attractive forces present between the particles present in lead nitrate. Because of this, the particles get separated from one another, and in a short time, the particles of lead nitrate get uniformly dispersed throughout the water. And this process is called dissolving or dissolution. So at the end, you will have a mixture of lead nitrate and water in which the particles of lead nitrate are uniformly spread throughout the water. Such a mixture is called a homogeneous mixture. And a homogeneous mixture of two or more substances is what is called a solution. So here we have a solution of lead nitrate in water. But remember, there is no chemical reaction taking place here. There is no chemical reaction between lead nitrate and water. This solution shows the properties of lead nitrate as well as water. So no new substance is formed during the formation of the solution, and the old substances are not going anywhere. Then what is the difference between solid lead nitrate and lead nitrate that is dissolved in water? The only difference being, in solid lead nitrate, the particles are very tightly held in their positions, so they cannot move freely. But in a solution of lead nitrate in water, these particles are free to move in water. Then, if water is not chemically reacting with lead nitrate here, then what is it doing? Here water does two things. One is that it is separating the particles of lead nitrate from one another and thereby allowing these particles to move freely. Secondly, it is providing a medium for these particles to move. So understand that formation of a solution is a physical change. And if you want, you can easily separate lead nitrate and water from this solution. Now, this particular solution is prepared by dissolving lead nitrate, which is a solid, in water, that is a liquid. But in general, solutions can be prepared by mixing substances in any physical state. You can prepare a solution of a solid in a solid, solid in a liquid, like we did here, liquid in a liquid, liquid in a gas, and so on. But if the solution is prepared by dissolving a solid in a liquid, then the solid is always called the solute, and the liquid is always called the solvent. So this solution has two components. One component is called solute and the other component is called solvent. And in all other cases, the substance that is taken in more quantity, that is present in more amount, is called the solvent. The one that is present in lesser amount is called the solute. And remember, sometimes there can be more than one solute, but you will always have only one solvent. For example, as a home remedy for dehydration, we dissolve both sugar and salt in water. Here, sugar and salt are both solutes and water is the solvent. But remember, in any solution, there can be only one solvent, but there can be more than one solute. But in general, we deal with solutions that contain one solute and one solvent. Now, a solution in which water is the solvent is known as an aqueous solution. We have a special name for solutions in which water is the solvent. It is called aqueous solution. Aqua means water. Solution in water is an aqueous solution. Now let us get back to this chemical reaction. To carry out this chemical reaction, we first dissolved lead nitrate in water to prepare an aqueous solution of lead nitrate. Similarly, we have to prepare an aqueous solution of potassium iodide by dissolving potassium iodide in water. Now, we mix these two aqueous solutions with one another. Because in these aqueous solutions, the particles are moving freely, and therefore a chemical reaction between them takes place easily and quickly. Now let us write a chemical equation for the reaction between these two solutions. Now what are the reactants in this reaction? Lead nitrate and potassium iodide, right? Lead nitrate is the solute in the first solution. Potassium iodide is the solute in the second solution. So here the reaction is taking place between the solutes of the solutions. And to indicate that these solutes are dissolved in water, or this reaction is taking place between aqueous solutions of these solutes, beneath their formulae we write AQ in parentheses. So this AQ means Here we took an aqueous solution of lead nitrate. Similarly, here AQ means we have an aqueous solution of potassium iodide, and this reaction is taking place between these two aqueous solutions. Remember, here I wrote S. This means solid lead nitrate, and this is solid potassium iodide. Now, if you mix these solids, it is difficult to carry out the chemical reaction. But if you mix their aqueous solutions, they readily mix with one another and a reaction takes place between them rather quickly and easily. Here, though water is available in the solution, it is not participating in the chemical reaction. So, we do not show water as a reactant because it is not participating in the reaction. Now, when these two react, one of the product you get is lead iodide, but lead iodide does not dissolve in water and it gets precipitated at the bottom of the container. So, you would get solid lead iodide. That is why I wrote S under the formula of lead iodide. And you would also get potassium nitrate, but potassium nitrate is soluble in water. So, you will have an aqueous solution of potassium nitrate and solid lead iodide as products of this chemical reaction between these two aqueous solutions. And you will come across many chemical reactions like this that are carried out between aqueous solutions. Solutions in which the solvent is water. And you will also come across many chemical reactions between solutions in which the solvent is not water. If the solvent is water, it is called an aqueous solution. If the solvent is not water, it is called a non-aqueous solution. Take this reaction for instance. Here these two reactants are not dissolved in water. They are dissolved in a solvent known as dimethyl sulfoxide. Therefore, these are non-aqueous solutions. To indicate that they are non-aqueous solutions, either you can write non-AQ below their formulae, or you can simply write SLN. SLN is an abbreviation for the word solution. So, to indicate a non-aqueous solution, either write non-AQ or SLN below its formula. So, this is an example of a chemical reaction taking place in a non-aqueous solution. Here we have another example of a chemical reaction taking place in an aqueous solution. And in this reaction, there are two reactants, acetic acid and barium hydroxide. And there are two products as well, barium acetate and water. Barium acetate is soluble in water, so it remains in the solution in which it is formed. So you will have an aqueous solution of barium acetate, and of course some liquid water is also formed as a product. Now this water is formed in aqueous solution, right? So should I write AQ or should I write L under this formula H2O? You have to write L, because if you write AQ, it means this compound H2O is dissolved in water. That does not make sense. You cannot say that water is dissolved in water. So pay attention to this. If water is one of the reactant or product in a reaction, don't put AQ underneath it. You have to write L. That is liquid water. I hope now you understand what I mean by the pun. The solution is solution. When we dissolve solids in an appropriate solvent like water or dimethyl sulfoxide or carbon tetrachloride or benzene or toluene, the particles of the solid become free to move. Therefore, it becomes easier to carry out chemical reactions between solutions. Now let us say we prepared two sugar solutions. The first solution is prepared by dissolving 5 spoons of sugar in sufficient amount of water to make 1 liter of the solution. The second solution is prepared by dissolving only 1 spoon of sugar in sufficient amount of water to make 0.1 liter of the solution. Now the question is, between these two solutions, which is more sweeter? Our intuition might suggest that because the first solution has 5 times more sugar than the second solution, the first solution must be more sweeter. But if you taste these two sugar solutions, you would understand that it is actually the second solution that is more sweeter. Why? That is because though the first solution has 5 times more sugar than the second solution, the volume of the solution in which the 5 spoons of sugar is dispersed in the first solution is 10 times more than the volume of the solution in which the 1 spoon of sugar is dispersed in the second solution. That means the sugar particles in the first solution are less crowded. They are dispersed over a much larger volume in the first solution, whereas the sugar particles in the second solution are more crowded because they are dispersed in way lesser volume. The total number of sugar particles in the first solution is way more than the total number of sugar particles in the second solution. But the crowdedness of the sugar particles in the second solution is more than the crowdedness of the sugar particles in the first solution. That is because the volume of the solution, the second solution, is way less compared to the volume of the first solution. That is why second solution tastes more sweeter than the first solution. So from this example, we understand that the sweetness of the sugar solution depends on the crowdedness of the sugar particles in the solution, not on the total number of sugar particles present in the solution. That means not on the total amount of sugar present in the solution. Between these two solutions, in this second solution, the crowdedness of the sugar particles is more. That is why it is more sweeter than the first solution. We have some technical terms to represent the crowdedness of solute particles in a solution. They are dilute and concentrated. A solution in which the solute particles are more crowded is known as a concentrated solution, and a solution in which the solute particles are less crowded is called a dilute solution. And we also have a name for the crowdedness of the solute particles in a solution. It is called concentration. So concentration of a solution is the crowdedness of the solute particles in that solution. The density of the solute particles in that solution. And a solution in which the crowdedness of the particles is more is called a concentrated solution, and a solution in which the crowdedness is less is called a dilute solution. Now, by using these words, we understand that the second solution is more concentrated than the first solution. But by how much? By how much is the second solution more sweeter than the first solution? So, if you want to quantitatively compare the concentrations of different solutions, you must be able to assign a number for the concentration of the solution. That is, a number to the crowdedness of the solute particles in a solution. And there are different methods to do this, and they are known as concentration terms. So, concentration terms are different methods to assign values to the concentration of a solution. That is, the crowdedness of the solute particles in a solution. Now, let us try to understand the various commonly used concentration terms. Now the question is, how do we assign a value to the concentration of a solution? By the way, what is the concentration of a solution? It is the crowdedness or the density of the solute particles in the solution. And as we discussed before, it obviously depends on two things. One is the amount of solute taken, and the other is the quantity of solvent in which it is dissolved, or the quantity of solution that is prepared. This is obvious, right? If you dissolve a given amount of solute in a lesser amount of solvent, then the crowdedness of the solute particles will be more. And if you dissolve the same amount of solute in more solvent, then the crowdedness of the solute particles will be less, because the solute is getting divided over larger amount of the solvent. Therefore, concentration of a solution is nothing but the ratio between the amount of solute and the quantity of solvent, or the quantity of the solution. In some concentration terms, the concentration of a solution is expressed with reference to the quantity of solvent, and in many concentration terms, the concentration of the solution is expressed with respect to the quantity of the solution. This is going to be a little confusing, so you have to pay careful attention to these differences. So every concentration term we are going to discuss is a ratio between the amount of solute and either the quantity of solvent or the quantity of solution. And in our discussion, I am going to represent solvent with the subscript A and solute with the subscript B. So, MA represents mass of the solvent, MB represents the mass of the solute, and so on. The first concentration term we are going to look at is called mass fraction. As the name suggests, it is the ratio between the mass of the solute and the mass of the solution. Pay attention to this. And the preparation of solution is a physical change. And according to law of conservation of mass, there is neither a loss or gain in mass during a physical or a chemical change. Therefore, according to law of conservation of mass, the mass of the solution must be equal to the sum of the masses of the solvent and the solute. So this will be equal to mass of the solute is mb, and I can replace mass of the solution with ma plus mb. So this is the mass fraction of a solution, ratio between the mass of the solute and the mass of the solution. Again, because it is a ratio between two masses, it is a dimensionless number, and it is generally denoted by m/m. There is no particular symbol for mass fraction. So it is generally denoted by m/m to indicate that it is a ratio between two masses. And because mass is independent of temperature and pressure, the ratio of masses is also independent of temperature and pressure. Therefore, the mass fraction of a solution is independent of temperature and pressure. It does not change with temperature and pressure, or it is the same at all temperatures and pressures. Now let us try to understand the meaning of mass fraction. Remember, this is the ratio between two masses. So when you determine mass fraction, you have to express these masses in the same units. If the numerator is in kilograms, denominator must also be in kilograms. If the numerator is in milligrams, the denominator must also be in milligrams, and so on. You cannot put their values in different units. Now, let us consider one part of the solution. What do you mean by one part of the solution? It could be 1 milligram of that solution, or 1 gram of that solution, or 1 kilogram of that solution, etc. That is what I mean by one part of the solution. That means MA plus MB is equal to either 1 milligram or 1 gram or 1 kilogram, etc. Then replace mass of the solution with one part. Then it becomes mass of the solute over one part of the solution. And you know what I mean by one part of the solution. So that means mass fraction m/m is nothing but the mass of the solute per one part of the solution. If it is 1 milligram, it is the mass of the solute in milligrams in 1 milligram of the solution. If one part is 1 gram, then it is the mass of the solute in grams in 1 gram of the solution, and so on. That is what mass fraction means. It is the mass of the solute per one part of the solution. Now, if mass fraction represents the mass of the solute per one part of the solution, then how do you get the mass of the solute per 100 parts of the solution? You have to multiply the mass fraction with 100, right? To get the mass of the solute per 100 parts of the solution, you have to multiply mass of the solute per one part of the solution with 100, and that is what we call percentage by mass. So Percentage by mass is nothing but the mass fraction of the solution multiplied with 100. Or in other words, percentage by mass is equal to the mass of the solute MB over MA plus MB, that is the mass of the solution multiplied with 100. This ratio is mass fraction. When multiplied with 100, you will get percentage by mass. Similarly, if you multiply mass fraction with a million, that is 10 to the power of 6, you would get parts per million. That is the mass of the solute in million parts of the solution. We use this ppm or parts per million in those cases where the amount of solute is very small compared to the amount of the solution. And you don't have to worry much about ppm, but understand that percentage by mass is the mass of the solute per 100 parts of the solution, and it is given by MB over MA plus MB multiplied with 100. Now we are ready to work out some examples on percentage by mass and mass fraction. This question says commercially ammonia is sold as an aqueous solution that is 28% by mass. What is the mass of ammonia present in 10 grams of this solution? How do we answer this question? Here, first you have to identify what the solute is. The solute is ammonia and the solvent is water because it is an aqueous solution. Now, we are given the mass of the solution, that is MA plus MB. It is given as 10 grams. And also we are given the percentage by mass of this ammonia solution. It is given as 28. Now, we have to figure out the mass of the solute, that is the mass of ammonia present in this solution. How do we figure that out? By using this expression. Percentage by mass is equal to mass of the solute, in this case ammonia, over the mass of the solution, that is MA plus MB multiplied with 100. Substitute these values in this expression to get the value of MB. Percentage by mass is 28.0, that is equal to MB over MA plus MB, that is the mass of the solution is given as 10 grams, and we have to multiply this with 100. Then MB will be equal to 28.0. Remember, this is dimensionless. Percentage by mass is dimensionless. Multiplied with 10.0 grams over 100. So simplify this to get the mass of ammonia in grams present in 10 grams of this ammonia solution. Now what do we have next? How do you prepare 350 grams of an aqueous solution containing 3.1% by mass of sodium acetate? Here again the solute is sodium acetate and the solvent is water. So we have to mix sodium acetate and water to prepare 350 grams of the solution. Now we have to figure out the masses of sodium acetate and water that must be mixed to make 350 grams of this solution. That's what this question is asking us to tell. How do we do this? We are given the percentage by mass of the solution. It is 3.1%. Again, it is dimensionless. Then we are also given the mass of the solution, that is MA plus MB, as 350 grams. we have to prepare 350 grams of this solution with this concentration. Now, can we first figure out the mass of the solute from this data? I think so. Percentage by mass is MB over MA plus MB multiplied with 100. Now, percentage by mass is given as 3.1. We have to figure out MB, and MA plus MB is the mass of the solution, that is 350 grams, and multiplied with 100. Now, MB will be 3.1 multiplied with 350 grams over 100. So, we already figured out the mass of the solute, that is the mass of sodium acetate needed to prepare this solution. And if you know MB, it is easy to figure out the value of MA, because MA plus MB is 350 grams, right? So MA will then be 350 grams minus MB, that is 350 grams minus 3.1 times 350 grams over 100. Simplify this to get the mass of the solvent, simplify this to get the mass of the solute, and mix those masses of the solvent and solute to make 350 grams of this aqueous solution of sodium acetate with this concentration. What do we have next? This question says hemoglobin contains 0.34% of iron by mass. Find the number of iron atoms present in 3.3 grams of hemoglobin. This is a question that appeared in a previous JEE examination. Now, assume that hemoglobin is a solution in which iron is the solute. So, we are given the percentage by mass of this solution, that is the concentration of the solution as 0.34%, and the mass of the solution is given as 3.3 grams, and we have to find out the number of iron atoms. To find out the number of iron atoms, first you must figure out the mass of iron present in 3.3 grams of hemoglobin. How do we figure that out? We know the expression for percentage by mass. It is equal to the mass of the solute, in this case the solute is iron, over the mass of the solution multiplied with 100. Substitute these values in this expression. Percentage by mass is 0.34. that is equal to mass of iron, that is the mass of solute, over mass of the solution is 3.3 grams multiplied with 100. Then MB will be equal to 0.34 multiplied with 3.3 grams over 100. Simplify this to get the mass of iron in grams. This is the mass of iron present in 3.3 grams of hemoglobin. Then how do you get the number of moles of iron? Divide the mass of iron with the relative atomic mass of iron expressed in grams. If the atomic mass of iron is 56.0 U, then the relative atomic mass of iron is simply 56.0. You have to drop this unit. And if you express that in grams, it becomes 56 grams. So you divide that with 56 grams to get the number of moles of iron. So it would be 0.34 multiplied with 3.3 grams over 100. And in the denominator now, we also have 56.0 grams. Cancel these two and simplify this to get the number of moles, which is dimensionless. To get the number of iron atoms, what do? You multiply the number of moles of iron with Avogadro's number, capital N, or N with the subscript 0. So it will be 0.34 times 3.3 over 100 multiplied with 56.0 and multiply this whole thing with 6.022 into 10 to the power 23. This is the approximate value of Avogadro's number. So this is the number of iron atoms present in 3.3 grams of hemoglobin if it contained 0.34% of iron by mass. Now the question is, where is this concentration term percentage by mass used? It is a very widely used concentration term. It is used to express the concentrations of commercially sold solutions. For example, the bleach solution that you buy in a supermarket expresses its concentration in percentage by mass. If you look at the label, it may say its concentration as 6.8% by mass. What does this mean? This means if you take 100 grams of that solution or that product, it contains 6.8 grams of bleach, and it is typically sodium hypochlorite. Similarly, all the acids that we buy for our chemistry laboratory are sold as highly concentrated aqueous solutions. They are called stock solutions. And the concentrations of all the stock solutions are expressed in percentage by mass. But all bases are sold as pure solids except for ammonia. Ammonia is one base that is sold as a 28% aqueous solution by mass. This is because ammonia is a gas at lab temperature, and ammonia gas has a strong odor and it is toxic. So it will be easier to handle it as an aqueous solution. So understand that percentage by mass is widely used to express the concentrations of commercially sold solutions. Now we are ready to move on to the next concentration term, that is mole fraction. Now isn't the name mole fraction similar to mass fraction that we discussed before? Of course it does. Therefore the definition of mole fraction is also similar to mass fraction we discussed before. All we have to do is replace wherever we have mass in the definition with number of moles to get the definition of mole fraction. So the mole fraction of solute in a solution will therefore be the ratio between the number of moles of solute and the total number of moles of solution. Pay attention to this. Now let us denote the number of moles of solute with Nb. How do you get the total number of moles of solution? Let us say the number of moles of solvent is Na, number of moles of solute is Nb. Then the total number of moles of solution is Na plus Nb. Is this right? It is right, because formation of a solution is a physical change. Therefore, there will be no change in the number of moles during the formation of a solution. So, the number of moles of solution must be equal to the number of moles of each component put together. This may not be true in case of a chemical change, but remember, formation of solution is a physical change. So during the formation of a solution, there is neither an increase in the number of moles nor a decrease in the number of moles, because the substances are not chemically reacting with one another. It is just a physical mixture of these substances. Therefore, I can say that the number of moles of solution is equal to the sum of the number of moles of each component in that solution. So this is the expression for the mole fraction of solute. Is this not similar to the expression we had for the mass fraction of the solute? It is. And we have a symbol to represent mole fraction. It is capital X, and the mole fraction of solute is denoted by XB. Remember, mole fraction is a ratio between number of moles. So it is a dimensionless quantity. Mole fraction is just a number without any units. Also remember that number of moles of a substance do not change with temperature and pressure. It is independent of temperature and pressure. Therefore, the ratio of number of moles is also independent of temperature and pressure. So the mole fraction of a component in a given solution is independent of temperature and pressure. It is the same at all temperatures and pressures. Now, can we also define the mole fraction of the solvent? Of course we can. Let us denote it with XA. It will be simply equal to the number of moles of solvent over the total number of moles in the solution. That is again Na plus Nb. Now, if you add the mole fractions of the solvent and the solute, what do you get? It will be Na over Na plus Nb plus Nb over Na plus Nb. Upon simplification, you will have the same value in the numerator and the denominator, and if you cancel them, you will get 1. So the sum of the mole fractions of all the components in a solution is equal to 1. Of course, that is by definition, right? Now, where is this concentration term mole fraction used? One example is it is used in case of a mixture of gases to calculate the partial pressure exerted by each gas in that mixture. To know the partial pressure of each gas, we need to know the mole fraction of that gas in that mixture of gases. And in those cases, it does not make sense to differentiate one gas as a solute, one gas as a solvent, and so on. So it is simply a mixture of gases where there is no differentiation between one component and the other component in that mixture of gases. Now, in general, if you have a mixture of several gases, then you can define mole fraction of each component in that mixture. It will be simply equal to the number of moles of that component over the total number of moles present in that mixture. And if you add up the mole fractions of all the components in that mixture, you will again get 1. Say if you have a mixture of gases called A, B, C, and so on, then the sum of the mole fractions of each of these gases in that mixture must be equal to 1. Now let us work out a simple example on mole fraction. Calculate the mole fraction of glucose and water in a solution that contains so many grams of glucose and so many grams of water. Here we have an aqueous solution of glucose in which glucose is the solute and water is the solvent. What is the expression for the mole fraction of solute? It is equal to the number of moles of solute over the total number of moles in the solution. That is Nb over Na plus Nb. Now, how do you get the number of moles of solute? We are given the mass of the solute present in the solution. So, it is mass given over the relative molecular mass of glucose expressed in grams. I think for glucose, the relative molecular mass is 180, expressed in grams is 180 grams. This is the number of moles of glucose. Then what is the number of moles of water? We are given the mass of water present in the solution. So divide the given mass with the relative molecular mass of water expressed in grams, that is 18 grams. Now you know Na and Nb. Substitute these values in this expression and simplify it to get the mole fraction of glucose, Xp. Then how do you get the mole fraction of water? That is the mole fraction of solvent. You know that Xa plus Xb is equal to 1. If you know Xb, then Xa is simply 1 minus Xb.